Every road you drive on, every building you enter, every bridge you cross, all of it begins with rock. Solid, unbreakable rock pulled straight from the earth. But here's the shocking truth. The United States produces over 1.5 billion tons of crushed stone every single year, more than almost any other material except water. That's enough rock to build entire cities from the ground up, again and again. So how does this happen? How do massive walls of stone get transformed into the foundations of modern civilization? Today, we're stepping inside the supergiant quarry mining industry, where America turns solid rock into cities through one of the most powerful industrial systems on Earth. Before we dive in, don't forget to like, subscribe, and turn on the notification bell so you never miss our deep dive documentaries into the industries that quietly power the modern world. The story begins deep beneath the surface, not underground, but in vast open pits carved into the earth. These are quarries, massive excavation sites where layers of rock that formed millions of years ago are now exposed and harvested. Across the United States, there are more than 5,000 active quarries producing billions of tons of material each year. These sites extract different types of rock, including limestone, granite, and basalt, each with unique properties used in construction. From the outside, a quarry looks like a giant staircase carved into the earth, with multiple levels descending into the pit. Each level, or bench, is carefully engineered to allow safe and efficient extraction. The process begins with drilling. Massive drilling rigs move across the quarry floor, boring holes deep into the rock. These holes can be several meters deep and are arranged in precise patterns. Then comes the most dramatic moment: blasting. Explosives are placed into the drilled holes and detonated in a controlled sequence. The blast fractures the solid rock, breaking it into manageable pieces. A single blast can release tens of thousands of tons of rock in seconds. The ground shakes. Dust fills the air, and what was once a solid wall becomes a pile of broken stone. But blasting is only the beginning. Once the rock is fragmented, giant excavators move in. These machines are massive, some weighing hundreds of tons, and equipped with buckets large enough to hold several tons of material at once. They scoop up the broken rock and load it into haul trucks. These trucks are among the largest vehicles on Earth. Some can carry 100 to 400 tons of rock in a single trip. Their tires alone can stand taller than a human. Day and night, these trucks move along winding quarry roads, transporting material from the pit to processing plants. And this is where raw rock begins its transformation. At the crushing plant, the process becomes mechanical and continuous. The first stage is the primary crusher. Here, large chunks of rock, sometimes over a meter in size, are fed into massive machines that break them into smaller pieces. The sound is deafening as steel jaws crush stone with immense force. From there, the material moves along conveyor belts to secondary and tertiary crushers. Each stage reduces the size further, turning large rocks into gravel, then into smaller aggregates. Conveyor systems can stretch for kilometers, moving thousands of tons of material per hour. Next comes screening. The crushed material is sorted using vibrating screens that separate stone by size. Different grades are produced, from large gravel used in foundations to fine particles used in concrete and asphalt. Each size has a specific purpose. Coarse aggregates are used in road bases and structural foundations. Medium-sized stones are used in drainage systems. Fine aggregates become part of concrete mixtures. Nothing is random. Every piece of rock is processed to meet exact specifications. From the quarry, the finished materials are loaded onto trucks, trains, or barges and transported to construction sites across the country. And this is where the scale becomes truly astonishing. To build just 1 kilometer of highway requires up to 20,000 tons of aggregate. A single large city can consume millions of tons of stone every year for construction, maintenance, and expansion. Without quarries, modern infrastructure would not exist. No roads, no buildings, no bridges, just raw land. But quarrying is not just about extraction, it's also about management. Operators must carefully plan each stage of excavation to ensure stability and efficiency. Environmental regulations require dust control, water management, and land restoration. Many quarries operate for decades, gradually expanding deeper and wider as material is removed. When a quarry reaches the end of its life, it doesn't simply disappear. In many cases, it is transformed. Some become lakes, parks, or recreational areas. Others are repurposed for industrial use or storage. This gives the land a second life, continuing its role in supporting communities. Technology is also transforming the industry. Modern quarries use GPS-guided equipment, drones for surveying, and automated systems to optimize production. Sensors monitor machine performance and material flow, reducing downtime and increasing efficiency. Some operations are even exploring autonomous haul trucks, reducing the need for human drivers in hazardous environments. Despite all this technology, the human element remains essential. Engineers design blasting patterns. Operators control heavy machinery. Technicians maintain equipment. And safety teams ensure that every operation is conducted responsibly. Because working in a quarry is not without risk. Heavy equipment, blasting operations, and constant movement require strict safety protocols. But with proper management, these operations continue to supply the materials that build the world around us. From solid rock deep in the earth to the concrete beneath your feet, the journey is one of transformation at an unimaginable scale. It is a process that turns millions of tons of ancient stone into the foundation of modern life. And it happens every single day. In the supergiant quarry mining industry, rock is not just extracted. It is engineered, processed, and transformed into the building blocks of civilization. If you enjoyed this journey into one of the most powerful industries on Earth, make sure to like, subscribe, and hit the notification bell so you never miss our next deep dive into the systems that shape our world. Thanks for watching. And remember, every city begins with a single piece of stone. Every year, the world produces more than 70 million tons of aluminum, a metal so light, strong, and versatile that it has become essential for airplanes, cars, buildings, packaging, and modern technology. But here's the part most people never see. Aluminum doesn't come out of the ground as shiny metal. It begins as a dull white powder called alumina, which must be transformed inside massive smelting plants using enormous amounts of electricity and extreme heat. In these facilities, rows of glowing furnaces stretch for hundreds of meters, silently converting mineral powder into rivers of liquid metal. Today, we're stepping inside a supergiant aluminum smelting plant to discover how alumina is turned into pure aluminum in one of the most powerful industrial processes on Earth. Before we dive in, don't forget to like, subscribe, and turn on the notification bell so you never miss our deep dive documentaries into the hidden industries that power modern civilization. Aluminum is one of the most abundant elements in the Earth's crust, yet it rarely exists as pure metal. Instead, it is found inside a reddish rock called bauxite, which forms through millions of years of tropical weathering. Bauxite itself is not aluminum metal, but a mixture of aluminum-rich minerals. To extract usable aluminum, this rock must first be refined into alumina, a fine white powder composed primarily of aluminum oxide. Once alumina has been produced at refining plants, it is transported to aluminum smelters, enormous industrial complexes designed to convert this powder into molten metal. Smelting aluminum requires extraordinary amounts of electricity, which is why these plants are often located near large power sources such as hydroelectric dams or major energy grids. The smelting process used around the world today is known as the Hall-Héroult process, a technology that has remained fundamentally unchanged since it was invented in 1886. Despite its age, it remains the only practical way to produce aluminum at industrial scale. Inside the smelter building, the first thing visitors notice is the scale. Long rows of rectangular furnaces, known as reduction cells or pots, stretch across huge halls, sometimes more than half a kilometer long. Each pot operates continuously for years at temperatures exceeding 950 degrees Celsius. These cells are filled with a molten electrolyte made primarily from cryolite, a mineral that helps dissolve alumina and lower its melting point. Without cryolite, the temperature required to melt aluminum oxide would be far too high for industrial equipment to handle. Alumina powder is gradually fed into these pots from storage silos above. When the powder enters the molten bath, it dissolves into the electrolyte, forming a mixture ready for electrolysis. Electrolysis is the heart of aluminum smelting. Massive electrical currents, sometimes more than 300,000 amperes, pass through each pot. Carbon anodes suspended above the liquid act as the positive electrodes, while the bottom of the pot serves as the negative electrode. When electricity flows through the bath, a powerful chemical reaction begins. The aluminum oxide breaks apart. Oxygen atoms combine with the carbon anodes, forming carbon dioxide gas, while pure aluminum atoms separate and sink to the bottom of the pot as molten metal. Over time, a pool of liquid aluminum slowly accumulates beneath the electrolyte. This glowing metal is incredibly pure, typically more than 99% aluminum. Operators monitor the cells carefully because the process must remain stable at all times. Sensors track temperature, voltage, and chemical composition inside each pot. Automated systems adjust the feeding of alumina to maintain the correct balance. If the concentration of alumina becomes too low, the electrical reaction can become unstable, so precision control is essential. Every few hours, specialized vacuum crucibles known as tapping machines arrive to collect the molten aluminum. A pipe is lowered into the pot, and suction draws the liquid metal into insulated containers. The aluminum emerges at nearly 960 degrees Celsius, glowing bright orange. These crucibles are transported to casting areas within the plant. Here, the molten aluminum is poured into molds to create large ingots, billets, or slabs, depending on the intended use. Some aluminum is cast into massive rectangular blocks weighing several tons each. Others are formed into cylindrical billets that will later be extruded into structural shapes. Still others are cast into rolling slabs used to manufacture aluminum sheets for automotive panels, beverage cans, and aircraft components. The cooling process transforms the molten metal into solid aluminum ready for further manufacturing. As the metal cools, its crystalline structure forms, giving it the strength and flexibility required for industrial applications. Aluminum's unique properties make it one of the most valuable materials in modern engineering. It weighs roughly 1/3 as much as steel, yet maintains excellent strength when alloyed with other elements. It resists corrosion naturally thanks to a thin oxide layer that forms on its surface. It also conducts heat and electricity efficiently, making it useful for power transmission and electronics. These characteristics explain why aluminum appears in almost every sector of modern life. Aircraft frames rely on aluminum alloys to reduce weight and improve fuel efficiency. Cars increasingly use aluminum components to lower emissions and extend electric vehicle range. Beverage cans are almost entirely aluminum because the metal is lightweight and easy to recycle. Perhaps most importantly, aluminum is infinitely recyclable. Unlike many materials, it can be melted and reused repeatedly without losing its quality. Recycling aluminum requires only about 5% of the energy needed to produce new metal from alumina. This makes aluminum recycling one of the most efficient material cycles in the world. However, producing primary aluminum from alumina remains essential to meet global demand. New aluminum is required for expanding infrastructure, renewable energy systems, transportation, and technology. The scale of an aluminum smelting plant reflects this enormous demand. Some facilities operate hundreds of reduction cells simultaneously, producing hundreds of thousands of tons of aluminum each year. Entire teams of engineers, electricians, and operators work around the clock to keep the process running smoothly. Power consumption is the single largest cost in aluminum smelting. A typical smelter uses as much electricity as a medium-sized city. For this reason, many smelters are located near hydroelectric power stations where renewable energy can supply the vast electrical needs. Environmental management is also a major focus of modern aluminum plants. Advanced filtration systems capture emissions from the reduction cells. Waste heat is monitored and controlled. New technologies aim to reduce carbon emissions by replacing traditional carbon anodes with alternative materials. Research is ongoing to make aluminum production even cleaner and more efficient. Engineers are exploring inert anode technology that could eliminate carbon dioxide emissions from the smelting process entirely. If successful, this innovation could dramatically reduce the environmental footprint of aluminum production worldwide. Despite these challenges, aluminum remains one of the most important metals of the modern era. Its combination of strength, lightness, recyclability, and corrosion resistance makes it indispensable across countless industries. The journey from alumina powder to molten aluminum is one of the most fascinating transformations in heavy industry. What begins as a mineral derived from ancient rock ultimately becomes the material that shapes airplanes, vehicles, buildings, and everyday products. Inside these giant smelting plants, thousands of tons of alumina are quietly converted into liquid metal every day. The process is intense, energy-hungry, and technologically complex. Yet it is also one of the foundational systems that keep the modern world moving. If you enjoyed this journey inside a giant aluminum smelting plant, make sure to like, subscribe, and hit the notification bell so you never miss our next exploration into the powerful industrial processes behind the materials we use every day. Thanks for watching. And remember, sometimes the most extraordinary transformations begin with something as simple as powder turning into liquid metal. Every year, thousands of tons of ordinary-looking rock are pulled from the ground across the United States, but hidden inside some of those rocks are crystals worth thousands, even tens of thousands, of dollars per kilogram. Yet here's the surprising truth. Unlike gold or copper, gemstones don't come from massive industrial mines moving entire mountains. Instead, they are discovered, selected, and transformed through a hidden network of small-scale mining, precision cutting, and high-value craftsmanship. What starts as a dull, rough stone can end its journey as a sparkling gem in a ring, a luxury watch, or even advanced electronics. Today, we're stepping inside this fascinating world, from raw rock to sparkling gems, the hidden industry behind America's precious stones. Before we dive in, don't forget to like, subscribe, and turn on the notification bell so you never miss our deep dive documentaries into the industries that quietly power the modern world. Gemstones have fascinated humans for thousands of years. Long before modern mining machines existed, Ancient civilizations searched rivers and mountains for crystals that seemed almost magical. In America, gemstone discovery accelerated in the 19th century during the Gold Rush era, when miners began noticing colorful crystals mixed in with the soil and rock. Over time, certain regions became known for specific gemstones: Montana for sapphires, Arizona for peridot, North Carolina for emeralds, and Arkansas for quartz crystals. But unlike metals, gemstones are not mined in bulk. They are rare, scattered, and often hidden deep within host rock. That means the journey begins not with massive excavation, but with careful exploration. Geologists study the land using maps, mineral clues, and sometimes satellite data. They look for signs of volcanic activity, ancient riverbeds, or mineral-rich veins, environments where gemstones are more likely to form. In many cases, exploratory drilling is used to confirm the presence of crystals underground. Once a site is confirmed, extraction begins. And this is where gemstone mining differs dramatically from traditional mining.